Hi, my name is Ken Edwards. I'm an owner and engineer with LMNO Engineering, Research and Software Limited. We are located in Athens, Ohio, USA, and this is our home page at www.lmnoeng.com. This video is going to be an analysis using our software and equations to analyze the experimental video of water discharging from a container through an orifice. And this video is slightly different than the other analysis video of the tank discharge calculation of the tank discharge experiment, because this video is using the trajectory information, the horizontal and vertical trajectory, in order to predict the head and the flow rate, and then to compare those head and flow rate predicted values with the experimental values. So we're going to use our discharge from a tank calculation, where we have our container here modeled as with the head being the distance from the center line of the orifice to the water surface in the tank, and B is the diameter of the orifice, which was measured as 0.25 inches. If this video looks a little bit small on your computer, you can use your right-click button and then select full page, and it will enlarge the video to the full size of your screen. So our diameter was 0.25 inches and our head was 4.75 inches. The horizontal trajectory to the point that we measured was 12.75 inches, and the vertical drop to that same location was 9.25 inches. And our hole was a sharp-edged orifice, and so that geometry will be useful in selecting the proper coefficients for the orifice equation. This is the calculation that we'll be using to compute the head and the discharge from the horizontal and vertical drop. But let's review the equations that are used in this calculation before we jump to the calculation. This is an equation for the velocity going out of the orifice, and it is a function of, actually it's the velocity at any position x and y as the water exits the orifice. So at our distance of 12.75 inches in the x direction and 9.25 inches in the y direction, the velocity at that position can be computed. This g is the acceleration of gravity, 32.2 or 32.174 is what our calculation uses, feet per second squared, and then x and y would need also to be in feet in order to compute the velocity in feet per second. Then this next equation can be solved for the head based on the velocity. So then once we have the velocity, we can then solve for the head and compute and compare that to our experimental value. And our experimentally determined value was 4.75 inches. Once the velocity is known, then it can be multiplied by the orifice area, which is based on 0.25 inches, times the contraction coefficient of the orifice to get the flow rate. For a sharp-edged orifice, the contraction coefficient Cc is 0.62 and the velocity coefficient Cv is 0.98. The product of Cc times Cv is C0, the orifice coefficient. And these terms are defined a little further down in our program right here, Cc, Cv, and C0. Well, now let's go back up to our calculation. And let's select, we want to compute flow rate Q and the head from the diameter and the x and y trajectory and the type of orifice. The type of orifice is sharp-edged. So let's come over here to some other initial selections, and we'll use English units with Q in gallons per minute and a circular orifice, And then instead of rounded orifice edges, let's select sharp edged orifice. And then we'll need to enter our horizontal distance and our vertical drop. Well, we measured those in inches, so let's convert them over to feet. And this page is a summary of our data. Our orifice diameter is 0.25 inches. Our head is 4.75 inches. This is what was measured in the experiment, which is 0.40 feet. And there's our flow rate, which was 0.5 gallons that we in our container, and it took 58 seconds to fill that. So the flow rate was 0.52 gallons per minute. Well, let's come down here to the trajectory information. Our horizontal trajectory was measured as 12.75 inches, which is 1.06 feet, and our vertical trajectory, vertical drop, was 9.25 inches, which is 0.77 feet. So let's go back to our calculation and let's enter the horizontal trajectory, change that from 10 to 1.06 feet, and let's change the vertical drop to what we measured of 0.77 feet. And our orifice diameter is 0.25. The CC and CV are built into the program and are selected by checking the sharp-edged orifice. The proper values for CC and CV are presented here, and then the product is C0. So we have all of our data entered here, so let's click to calculate. And I'll come back to this red message in a minute, but the program computes the head of 0.3798, or to round it, 0.38 feet, so let's write that number down. And then the discharge is computed as 0.4596, or to round that to 2 decimal places, 0.46 gallons per minute. So let's go over back to our data page. And so from our calculation, our head was 0.38 feet and our discharge was 0.46. So those numbers are direct from over here. So I simply copy them over to this page. And so then we can compute the percent difference between the measured and computed heads, which is 5.3%. And then the percent difference between the measured and computed flows is 13%. And these heads and flows are based on the trajectory data. The X and Y trajectory data that we measured are all that you need to compute the head and the flow rate, as you could see on the equations that were used in our calculation here. Again, to review, your X and Y give you the velocity. Once you know velocity, you can compute the head. Once you know the head, you can compute the flow rate. So let's come back. So whether these percent differences are acceptable depends on what you want to use the results of the calculation for, or the results of the experiment. And you may want to run a more tightly controlled experiment. So let's look at our sources of error. Our head measurement was probably plus or minus 0.25 inches, which is 0.02 feet, and the flow rate volume was recorded probably to about plus or minus 0.5 pints, which is plus or minus 0.06 gallons. And the time for the flow rate measurement was probably about plus or minus 2 seconds. Note that our orifice equation gave us a message saying that it's inaccurate because the diameter is less than 1 inch. If we come down, scroll down, the equations are valid for a diameter B greater than 1 inch and a head greater than 4.17 feet. And so our calculation, if our diameter had been greater than 1 inch, we would have got the head error message that we were less than 4.17 feet. The calculation only gives one error message at a time. And so then that could be a source of error in our results. And also we could have error in the CC and CV values. Well, those values were determined by many researchers over the years and were determined to be valid for a sharp-edged orifice. But also they are best to be used if your head is greater than 4.17 feet and your diameter is greater than 1 inch. So even though this is the most commonly used equation for discharge from an orifice, even if you don't satisfy the head and diameter criteria, you may see some error when using this equation if your head and diameter don't strictly satisfy these criteria. Well, this concludes our video. If you have any questions, feel free to call me, Ken Edwards, at area 740-592-1890 in the USA, or contact me by email at lmno@lmnoeng.com. Thank you for watching.